You ever wonder how your computer actually finds a single file when you have thousands of them? Well, a lot of the time, it starts with a method that's so simple, you probably use it every day without even realizing it. Today, we're going to break down the original finder, the linear search.
Okay, let's start with a real-world example. Imagine you're standing in front of a bookshelf, but it's a complete and total mess. The books are not in alphabetical order, not sorted by genre, nothing. And you're looking for one specific title. What's your strategy?
Yeah, you don't really have much of a choice, do you? You have to start at one end and look at every single book spine, one by one, until you either find your book or you hit the other end of the shelf. At its very core, that is exactly what a computer does when it performs a linear search.
And that brings us right to the official definition. Linear search, which you might also hear called sequential search, is the simplest way you can possibly find an item in a collection. You just check every single element in order until you get a hit or you've run out of things to check. No tricks, no shortcuts, just pure persistence.
So, how does this whole bookshelf idea translate into actual logic a computer can follow? Let's break down the step-by-step mechanics. The logic is really just a simple loop that perfectly mirrors our bookshelf search. You start at the very first item, compare it to what you're looking for, and if it's a match, awesome, you're done. If not, you just move to the next item in line and do it all over again, repeating the process until you either find what you're looking for or you run out of items. And here's how that logic translates directly into some Java code. You see that for loop? That's basically us walking down the bookshelf, checking each element one by one. The if statement inside is the moment we stop and check the book's title. If we get a match, we return its position, or its index. And if the loop finishes without finding anything, we return -1, which in the programming world pretty much means not found. Okay, so linear search is simple. We've got that. But is it efficient? In computer science, efficiency usually comes down to speed. So let's analyze the performance of this very straightforward approach. The thing is, the performance of a linear search can swing wildly between two extremes. The absolute best case, the item you're looking for is the very first one you check. One look, and you're done. Easy. The worst case, it's the very last item in the list, or even worse, it's not in the list at all. In that scenario, you have to look at every single item. We measure this efficiency using something called big O notation. That best case is what we call O of 1, or constant time, because it takes the same single step no matter how long the list is. The worst case, however, is O of n, or linear time. This just means the time it takes grows in a straight line with the number of items, which we call n. So a list with 100 items could take up to 100 steps. And since on average you'll probably check about half the items, we consider the average case to be O of n as well. Now, given that it has the potential to be pretty slow, you might be wondering, why do we even bother with linear search? That's a totally fair question. And the answer is all about knowing when to use the right tool for the job. So let's explore the scenarios where this simple algorithm is actually the best choice. Linear search really shines in a few key situations. First, its biggest advantage by far is that it works perfectly on unsorted data. For small lists, the speed difference compared to more complex algorithms is so tiny it doesn't matter, which makes its simplicity a huge plus. And finally, sometimes it's the only practical way to search certain data structures, like linked lists, where you literally have to go through items one by one anyway. And this really sums it all up. For any unsorted data, linear search is the most direct and logical option you have. Its versatility comes from the simple fact that it makes zero assumptions about the order of the data, just like with our messy bookshelf. To really appreciate its strengths and weaknesses, let's put linear search head-to-head with a much faster alternative, binary search. This comparison is going to make the trade-offs crystal clear. The difference is pretty stark. Binary search is incredibly fast, O log n, but it has one massive, non-negotiable requirement. The data absolutely must be sorted. Linear search is slower, at O n, but it requires zero preparation. So think about it. If your data is unsorted and you only need to search it once, sorting the whole thing just to use binary search would take way more time than just using a simple linear search from the get-go. So, what are the key takeaways here? Well, linear search is simple, versatile, and super easy to implement. It's the go-to choice for small lists or any unsorted list. Yes, its performance gets worse as the list gets bigger, but its importance as a foundational concept just can't be overstated. It's the starting point for understanding all the more advanced search methods. And this leaves us with one final thought.
In a world that is obsessed with optimization and speed, linear search is a great reminder that sometimes the simple and correct solution is actually the smartest one. It's a powerful lesson in practicality over pure performance.